Good day, students. Today we are starting to study a new discipline for you. Today we are going to start to talk about immunology. This semester we will study both disciplines, microbiology and immunology. In the end of this semester, you will have microbiology exam and immunology credit. But firstly, I want to say that you will have 9 lectures in immunology this semester, then 9 practical classes. Every practical class, you will have oral test, and in the end of May you will have a credit. What should you have for credit? Credit in immunology is given like in microbiology. If you have a lecture and practical copybook, if you have your grades or points for every class except 2, you will have it automatically. If you don't get immunology credit, you will not be allowed to have exam in microbiology and in other disciplines. I hope you understood that if you don't pass credits, you are not allowed to have exams. Immunology practical classes will be on the second week, microbiology practical classes on the first week. So the second week we will have immunology practical classes. On the first week we will have microbiology practical classes. For immunology practical classes you must have practical copybook. Please don't write in your microbiology practical copybook. You must have different copybooks. So let's start. The first one that we should say, what is immunology? From the name of this science, you may understood that immunology it's science about immunity. You know what is immunity from microbiology? It is ability to resist particular antigens. So, scientific definition of immunology is like this. Immunology is a science that studies mechanisms of self-defense of organism against antigens in norm and pathology. It is study of mechanisms of our defense of our body against antigens in normal conditions in healthy persons, and pathology means in sick patients. Immunology deals with the physiological functioning of the immune system in states of both health and disease. So immunology studies work of immune system, activity of immune system in healthy individuals and in sick patients. Then immunology works with malfunctions of the immune system in immunological disorder. Malfunctions or dysfunctions of immune system. In immunological disorders that are caused by dysfunction of immune system, for example in autoimmune disease or in immune deficiency. And immunology also works with physical, chemical and physiological characteristics of the components of the immune system in vitro, in situ and in vivo. In other words, immunology studies parameters and characteristics of cells of immune system or molecules of immune cells in vitro, means in the laboratory, in the tube, in situ, in tissues, and in vivo, in living organism. Before we will start to talk about immunology, we should say how immunology developed, how it developed, and how this discipline arisen. The first scientist who must be discussed in this question is Edward Jenner. Edward Jenner was so-called father of immunology. What does it mean? He made a first experiment with cowpox that showed resistance of human organism against some diseases. What did he do? Edward Jenner took material from a burst pustule, like pus, discharge of woman with cowpox, and then he injected material into the boy's body, and this body became protected against cowpox. We can say that it was similar to vaccine. Sure, it was not vaccine that we use today, but it was similar to vaccines. It was a pro-vaccine. We can say that it is precursor of vaccine. So Edward Jenner showed that people who contacted with pathogens became resistant to this antigen. Then the next scientist was Louis Pasteur. You know his name from microbiology. Louis Pasteur was a famous great French scientist, bacteriologist, who is considered as a father of microbiology, as a founder of microbiology. Louis Pasteur discovered the first alternative vaccines for anthrax and rabies. Anthrax is a bacterial infection and rabies is a viral infection. After that, these anti-anthrax and anti-rabies vaccines were used in all countries from all over the world. Later, in 1880, Ilya Mechnikov, who was a Russian scientist, discovered phagocytic cells that ingest microbes and foreign particles. So he started to work in field of cellular immunity. He proved that some human cells are able to engulf and ingest foreign cells, like bacteria, for example. Then he called these cells phagocytes. So Ilya Mechnikov was a founder of phagocytic theory of immunity, or phagocytic or cellular immunity. At the time, another scientist who worked in Germany, Paul Ehrlich, developed supposed presence of antibodies in the blood. Paul Ehrlich, unlike Mechnikov, said that the main role in immunity is in antibodies. So he said that human fluid like serum took a great role in resistance, in protection. So he called his theory of immunity as a humoral theory or humoral immunity. Mechnikov and Paul Ehrlich discussed they were not agree with each other, but then in 1905 both Mechnikov and Paul Ehrlich were awarded with a Nobel Prize for their works in immunity, for their discoveries in immunity. Both Mechnikov and Paul Ehrlich were right in their works, because there are two parts of immunity in our organism: is cellular, and another one is a humoral immunity. Another main step in history of immunology was in 1989, when the World Health Organization announced that smallpox was eradicated from the world. During about 40 or 50 years, all countries used obligate vaccination of every person. So it was seen that smallpox was eradicated. Sure, today we can find some sporadic cases of smallpox in some regions of Africa and some poor, very poor regions, but mostly this disease was eradicated. Then we should talk what is immunity and how is it classified. You know this question from microbiology. This question is mostly this. Once more, immunity is the ability to resist a particular antigens to microorganisms or tumors. I want to remind you that antigens, these are foreign macromolecules that, for example, are microorganisms or tumors that cause immune response in human organism. Immunity can be classified into innate immunity and acquired. Innate immunity is present in every person, in every patient, in every child, from the birth. These are mostly mechanical barriers, like skin, for example. Then this is the tears, a low pH of stomach, that is a chemical barrier, because acidic conditions are harmful for bacteria, they kill bacteria. A respiratory cilia that eradicate bacteria from nose, from respiratory tract. Normal flora of gut, of intestine also take part in innate immunity. So innate immunity is present in every person from the birth. The another part of immunity is acquired. Acquired can be divided into natural immunity, natural acquired, and artificial acquired. Natural, both natural and artificial immunity may be classified into active and passive. The first one that we are talking is natural active immunity. Natural active. It means that this immunity is working by itself, by activation of immune cells, by natural way. For example, natural active immunity arises during exposure to diseases. Then antibodies are produced. So natural active immunity develops after diseases that produce lifelong immunity. For example, after such diseases as whooping cough, diphtheria, poliomyelitis, influenza. After these diseases, human organism produce natural active immunity. Natural passive immunity means that a human organism doesn't activate immune cells. And this immunity is acquired by passive way. What is it? It is transmission of antibodies from mother to child. Passive way. Immune cells of child's organism are not activated. Newborn gets antibodies from mother via breast milk or via through placenta. That's why it is very important, to feed the newborn via breast milk, because it's a complex, it's a mixture of great amount of antibodies. These antibodies protect newborn against some diseases. During the first 2 or 3 months, child's immune system is not so active. It's not able to protect himself or herself. This is why it's very important. The another part of immunity is artificial immunity. Artificial can be also active and passive. Artificial means that this immunity is acquired by artificial way. Artificial active is produced by vaccination, when we inject low dose of antigens, attenuated vaccine or killed vaccine. And artificial passive includes immunization, when we introduce antibodies in the body. So artificial active means that immune system starts to work when antigens enter the human organism. There is immune response. In artificial passive, immune cells are not activated, antibodies are directly injected into human organism, into the blood. Artificial active immunity is developed during some weeks or months. For example, after vaccine, if we vaccinate the patient via vaccine against tick-borne encephalitis, it produces immunity after 9 months. Or, for example, against COVID, if we vaccinate the person against COVID-19, immunity is produced after 40 days. A human immune system needs about 40 days to produce antibodies. But when we inject serum, human organism gets protection immediately. But if we inject serum, this protection is not so long as in vaccination, because foreign antibodies disappear during some weeks. Vaccination provide immunity for some years, about, for example, some vaccines for 6 years. Immunity also can be divided into antibacterial, antiviral, antitoxic, antiprotozoan, antifungal, and transplantation immunity. This classification is based on the type, on the origin of antigen. So if antigen is a bacteria, this immunity is antibacterial. If it's virus, antiviral. If it's toxin, it's antitoxic. In the end of this semester, in the last lecture, we will make conclusion about different types of immunity. We will talk what are differences between antiviral, antibacterial immunity, or transplantation immunity, when we can see graft rejection or destruction of transplanted tissues and organs. Then, in another classification, we can divide immunity into cellular and humoral. I've started to talk about it when I told you about history of immunology, about Metchnikov and Paul Ehrlich. Cellular immunity is includes activation of cells that are called phagocytes. So the main process of cellular immunity is phagocytosis. Humoral immunity includes antibodies in human serum. The another classification includes sterile and non-sterile immunity. Sterile immunity active even in the absence of the pathogen in human organism. It means that sterile immunity is present during all the life of the patient. In other words, it's similar to natural active immunity. After disease, patient has lifelong immunity. We discussed it in microbiology. Examples of sterile immunity: diphtheria, whooping cough, scarlet fever. A non-sterile immunity is another one. It's active only in the presence of the pathogen. While pathogen is present in human organisms, antibodies are present and immune system human organism is protected. When pathogen is eradicated from human organism, antibodies disappear and human can have the same infection once more and once more. It's a lot of infection caused by staphylococcus, it's gonorrhea, for example. Then, we have said that the main role of immunology is study of immune system. What is immune system? What is structure of immune system? Before we will talk about organs of immune system, we should say about its structure. So immune system includes organs. Organs produce cells, and cells synthesize molecules. What are these molecules? They include immunoglobulins or antibodies and intracellular adhesion molecules, for example, cytokines, that regulate activity of immune cells. Once more, immune system includes organs that produce cells. Cells are produced by organs, and molecules are produced by cells. What are organs of immune system? There are two main groups of immune organs. It's primary organs and secondary organs. Primary organs includes just two ones, as this is thymus and bone marrow. Secondary organs includes lots of main immune organs like adenoids, tonsils, lymph nodes, spleen, Peyer's patches, appendix, and lymph nodes. Let's talk deeper about them. Primary organs include thymus and bone marrow. The main functions of these organs are: the first one, formation; then the second one, antigen independent differentiation; and the third one, proliferation of immune cells. So what happens in thymus and bone marrow? Immune cells are formed, then they are differentiated without presence of antigen, in the absence of antigen. Antigen independent means in the absence of antigen. And they proliferate. Their primary proliferation occurs there. Thymus is the central or primary organ for the differentiation and functional maturation of T cells. So remember that T cells are called T cells because they are produced in thymus. The size of the thymus is age-dependent. It reaches a maximum weight around 10th year of life and then undergoes a continuous process of involution. That's why in old patients, amount of T cells extremely decrease, and immune protection is not so active in old patients. Where is it located? Thymus. Look here. Thymus is located in the upper front part of the chest, behind the sternum, and between the lungs. In the upper front part of the chest, behind the sternum, between the lungs. The another primary organ of the immune system is the bone marrow. In birds, B cells differentiate in bursa of Fabricius, its specific immune organ. That's why B cells are called B cells. In human, hematopoietic cells in fetal liver and in adult bone marrow give rise to B cells. So B cells are produced in bone marrow in adult person and in fetal liver in a newborn. The another group of organs, these are secondary immune organs. The main functions of secondary immune organs are antigen-dependent or antigen-stimulated differentiation and proliferation of immune cells. It means that immune cells are proliferated and differentiated when antigen is present, and they are stimulated by the presence of antigen. Secondary immune organs includes a lot of organs. That's why they are classified. They are classified into two big groups. These are encapsulated organs, and another group are mucosal associated lymphoid tissues. So encapsulated organs includes lymph nodes here, or here, and spleen. Mucosal associated lymphoid tissues includes diffusive lymphoid tissues and organized lymphoid tissues that have follicular structure. Diffusive mucosal associated lymphoid tissues includes aggregation of lymphocytes, phagocytes, and plasma cells in the lungs, bronchus associated lymphoid tissue, gut associated lymphoid tissue in intestine, lymphoid tissue found in urogenital tract, it is not shown here, nasopharyngeal associated lymphoid tissue. These are diffusive tissues. But also we can see that some lymphoid tissues are organized in follicles. These are Valdeir's Pirogov's ring that includes adenoids and tonsils in throat. Peyer's patches in small intestine. These are large aggregates of lymphoid tissue found in the small intestine. And appendix. Then we should talk about role of blood cells in immunity. Blood cells take a great role in immunity. All blood cells arise from one pluripotent stem cell that develops in myeloid progenitor or lymphoid progenitor. So myeloid progenitor then develop into blood cells like erythrocytes, basophils, eosinophils, neutrophils. We are interested in basophils, eosinophils, and neutrophils. These cells, these white blood cells, take a great role in immune protection. All white blood cells can be divided into granulocytes and agranulocytes. Granulocytes are also called polymorph nuclear leukocytes. They have specific granules in their cytoplasm, that's why they are called granulocytes, and they have a segmented nucleus, a nucleus that is segmented into 3 lobes or 3 parts. That's why they are called polymorph nuclear. Granulocytes include such cells as neutrophils, eosinophils, basophils, and mast cells. Mast cells are similar to basophils, but they are present in tissues. Agranulocytes are also called mononuclear leukocytes. They don't have granules in cytoplasm, and they include lymphocytes, monocytes that are present in the blood, and macrophages in tissues. Let's come back to them. Granulocytes, these are granulocytes. We can see granules, colored granules in the cells, and these are agranulocytes that include lymphocytes, T lymphocytes and B lymphocytes. For example, monocytes and macrophages. They are not shown here. Let's talk firstly about granulocytes. Neutrophils are one of the main group of white blood cells. They are the first responders to inflammation. They are activated first in inflammation process. They are predominant cells in pus, accounting for its whitish yellowish appearance. You know that pus has white or yellow color because of neutrophils. The another one are eosinophils. Eosinophils secrete anti-inflammatory substances in allergic reactions, and they play an important role in the killing of parasites. Great role in killing of large antigens as parasites or protozoan are in eosinophils. Basophils are found in blood or in tissues. If they are present in tissues, they are called mast cells. Basophils have a great role in allergic reactions. They produce mediators, allergic mediators, such as heparin, histamine, serotonin that leads to anaphylaxis and allergy. Allergy is also protective mechanism of human organism. You will talk about it in pathophysiology next year. Granulocytes. I remind you that granulocytes don't have granules. These are lymphocytes and monocytes or macrophages. Granulocytes in the blood circulation are lymphocytes, lymphatic cells, T and B cells, and monocytes. Granulocytes that leave circulation, blood circulation, and differentiate are called macrophages. So macrophages are present in tissues. Monocytes are present in the bloodstream. Macrophages are highly phagocytic. Macrophages in tissues proliferate and survive for months, for long period. And in every tissue there are specific macrophages that provide phagocytosis there. For example, Kupffer cells are present in liver, alveolar macrophages are present in the lungs, Langerhans cells are present in the skin, osteoclasts are present in the bone, and so on. The main functions of macrophages are phagocytosis, killing of pathogen, and cytokine production. We will talk what are cytokines. These are specific proteins that activate different types of immune cells. So we have just said about lymphocytes, about white blood cells and their role in immune protection, about granulocytes that are lymphocytes and macrophages. And now let's talk about lymphocytes. Firstly, lymphocytes arise from lymphoid stem cells that develop into lymphoblasts, and lymphocytes are differentiated into B cells, T cells, and natural killer cells, NK cells. So T cells provide cell-mediated immune response. B cells provide humoral immune response. B cells, the main role of B cells is the production of plasma cells that produce antibodies that are present in serum. Serum is a fluid, so from Latin language fluid is called humus. Humus, it's fluid from Latin language. So main role of B lymphocytes, B cells, is production of antibodies. Another group of lymphocytes are null cells that neither T cells nor B cells. For example, natural killer cells, they are not included in neither group of T cells or B cells. A cells, these are macrophages that have the main function of presentation of foreign antigen to T helpers. And dendritic cells also present antigen to T helper. Let's talk about T cells and B cells. T cells and B cells are classified into some groups, and this classification is based on the presence of specific molecules that are called CD, or clusters of differentiation. CD are surface molecules called clusters of differentiation. They are markers, specific markers that reflect stage of differentiation and functional properties of the cell. What I mean? Firstly, CD are glycoproteins, and there are some types of this glycoprotein that is present in T cells and B cells and it provides their differentiation and their functions in immune system. Today we know about more than 18 types of CD markers. They are called CD1, CD2, CD3, CD4, CD6, and so on. If we talk about T cells, they have CD3 molecules, CD4, and CD8. CD3 molecules are present on the surface of all T cells. They are markers of T cells. B cells don't have CD3 molecules. CD4 molecules are present on the surface of T helpers that include Th1 and Th2. I will tell what is it. CD8 are present on the surface of T killers or T suppressors. B cells have CD19 and CD21. CD19 and CD21 are markers of B cells. So, about T cells and their markers. T cells that have CD4 markers, CD4, these are T helpers. They are helpers from the name of these cells. We can understand that they don't kill antigen, don't destroy antigen, don't kill bacteria. They just help in immune response. So CD4 cells that are T helpers secrete lymphokines which act on other cells involved in the immune response. So they activate other cells. Which cells are activated? There are two groups of T cells, Th1 and Th2. Th1 activate cytotoxic lymphocytes that are CD8, these cells, and macrophages. So it induces cell-mediated immune response and inflammation. Cell-mediated means that these cells kill pathogen, cytotoxic lymphocytes and macrophages. Cytotoxic lymphocytes release cytotoxic substances and destroy pathogen. Macrophages engulf and digest pathogen. It is called cell-mediated immunity. Th2 activate B cells. That is humoral immunity. B cells then produce plasma cells that secrete antibodies. So T cells that are T helpers, CD4 cells, are one of the main regulatory cells in immunity. T cells that have CD marker CD8 are called cytotoxic lymphocytes or CTL. They cause lysis of infected cells. They produce cytotoxic substances outside and destroy a virally or virus infected cell or tumor cell, because tumor cells are transformed. They are also antigens for human organism. We have just said about T cells and B cells, and there is an intermediate group that is called null cells. They are neither B nor T cells. They don't have any surface markers. They don't have any CD markers on their surface. They attack pathogens and abnormal cells. Abnormal cells, I mean transformed cells like tumor cells or maybe virally transformed cells. And one of the main group of null cells are natural killer cells. From the name, you may understand their main function: killers. They kill. How do they kill pathogens and abnormal cells? Natural killer cells release cytolytic substances outside, so they destroy virally transformed cells, certain tumor cells, and take part in graft rejection in transplantation. Graft rejection is the destruction of transplanted organ or tissue. So we have said about immunity, about classification, about immune organs, primary and secondary, about blood cells and immune cells. Now we should make a conclusion how all cells communicate with each other in immune system, in human organism. We should talk about immune response. Immune response is the response of immune system to antigen. In other words, it's interaction of T cells and B cells during immune response when any antigen, when some antigen enters the human organism. In this scheme, you can see interaction of cells and main stages of immune response. Immune response develops when any antigen enters the human organism. Immune response includes a non-specific response and stages of specific response. Non-specific means that immune cells don't choose what is this antigen. They attack, they destroy any antigen that enters human organism. Specific immune response, specific stages of immune response includes activation of specific cells that are antigen dependent. These stages reflect what happens in our organism when microorganism enters the human body. Let's talk about it. Firstly, some pathogen enters the human organism, for example, virus or bacteria. The first cells that are activated, that attack the pathogen, are macrophages. I remind you that macrophages are present in tissues, monocytes are present in the bloodstream. Macrophages engulf pathogen and digest it. Then macrophage digested into small fragments, into small parts, into antigens. You remember, for example, that bacterial cell have O antigen, H antigen, that is flagellar antigen, K antigen, that is capsular antigen. So whole bacterial cell must be destroyed into small particles, into antigens. And these antigens are presented by macrophage on the surface of the cell to T helpers. T helper cells don't kill pathogen. They have a lot of receptors to recognize antigens on the surface of the macrophage. You know that there are two groups of T helpers, Th1 and Th2. Th1 produce specific lymphokines, specific substances that activate T killer cells or cytotoxic lymphocytes. These CD8 cells, cytotoxic lymphocytes release cytotoxic substances and destroy infected body cell. Th2 produce specific cytokines, interleukin, for example, to activate B cells. B cells produce plasma cells, and plasma cells secrete antibodies. Antibodies specifically bind to antigen and destroy it. Macrophages also take part in full destruction, in full killing of antigens, because antibodies have a great role, have a great function as opsonization. It's engulfment of phagocytosis. Macrophages, success of macrophages, phagocytosis depends on the presence of antibodies. If antibodies are present, antigen are present on the surface of antigen, it improves engulfment of antigen by macrophages. One part of B cells differentiated into memory cells. Memory cells have specific receptors on their surface that store information about characteristics, about antigens of the pathogen. Memory cells circulate in human bloodstream during a long period, during several years, and even during all their life. And when the same antigen, the same bacteria or virus enters human organism once more, memory cells are activated, and they produce B cells, and they produce plasma cells and antibodies very, very fast. So the time of immune response is shorter in secondary response than in primary response. Process of recognition of antigens by T helper cells occurs mostly in lymph nodes, in local lymph nodes. So all T cells and B cells are present there. That's why maybe you know that in infection we can see enlargement of lymph nodes. It occurs because of active differentiation and proliferation of immune cells there, of T cells and B cells. For example, if it's infection of respiratory system, of upper respiratory tract, these are lymph nodes in throat. So these processes occur when any pathogen enters the human organism, enters the human body. And you may understand what happens when any bacteria or virus enters your organism. Actually, the time of this immune response from an entry of pathogen up to production of antibodies lasts about 7 days in primary immune response, when microorganism enters in human body primarily, and it is shorter in secondary immune response. It is shorter, it's about 3-4 days in secondary immune response. So that's all for this function, for this lecture. You should prepare this lecture for the first practical class, that will be in the first week. We will study it will be from the 7th of February. I will upload the link for this class, for this lecture, on the portal for every group. What about reworking? What about recredit? You may rework starting from the 7th of February. The official date of our microbiology recredit will be chosen later. I will tell you, but you may rework from the 7th of February. Now that's all. Thanks for your attention. Goodbye.